Welcome to Data Science with EJD. Still talking about clustering under unsupervised learning, under machine learning. So far we've talked about k-means clustering, we've talked about hierarchical clustering, and here we're talking about density-based spatial clustering of applications with noise. That's DBSCAN for short. Um, so this will give us an idea into that. But before I do that, let me make this shorter to look at. Yeah, I think that's about it for now. Yeah. Okay. So DBSCAN is a density-based clustering algorithm designed to discover clusters of arbitrary shape based on the notion of density connectivity. Unlike centroid-based method like k-means, which partition data into convex clusters, DBSCAN groups together points that are closely packed or like in dense regions and label points in low density regions as noise outliers. So the closer together the data points are, the more likely they are to be grouped as as a dense region. Whereas if you have points, data points standing on their own, this can be seen as noise or outliers. So core concepts and terminology of DBSCAN is you have the epsilon, that's the neighborhood radius around the point within which neighboring points are counted. You have minimum point, that's minimum number of points required to form a dense region or core point. Then you have the core point too, which is the point with at least minimum points neighbors within distance of epsilon. Then you have border points, a point that is not a core point but lies within epsilon of a core point. Usually in mathematics, right, epsilon is seen as a positive number that is very small, right? Maybe like 0.001 or something like that. So it's very small, but it's not negative. Then you have noise point, a point that is neither a core nor a border point. So any point that falls outside the core point or a border point is considered an outlier. So they are considered like some kind of noise or outlier in the data set, some kind of distraction, so to speak. Then the algorithm overview for each point, count how many points fall within its epsilon neighborhood. So if you're taking data point that are like 0.01 distance from every point, so anything outside of that point does not fall into the region, right? So you want to identify core points. So points with greater than or equal to minimum point neighbors. Then for each core point, form a cluster by connecting all density reachable points. That's points reachable through a chain of core points, right? So points not reachable from any core points are labeled noise. So if you say you have a data point and you want to take every point that is like 0.001 distance from it, so anything that doesn't fall with, by the time you do that for all data points, anything that doesn't fall within that range is seen as an outlier. Now we can do parameter tuning for this because I mean you can already imagine it's a lot of work. Choosing epsilon and minimum points correctly is crucial. So minimum point, a rule of the thumb is minimum point is two times number of dimensions. So larger values reduce noise sensitivity but require denser clusters, right? So the epsilon you have to choose based on domain knowledge or using the k distance plot. So you have to compute distances to each point's minimum points nearest neighbor. So plot this sorted distances, the k distance graph, then identify the elbow points indicating the natural cutoff distance for epsilon. Now we talked about the elbow method when we talk about k-means and of course the silhouette score, So in the elbow idea, it's that point where any additional thing you have add to it doesn't really change much. But I particularly like the silhouette score because it shows you the optimal number of clusters you should have in your clustering. Okay. So how do you handle noise then? Handling noise, DBSCAN explicitly identifies noise points which do not belong to any cluster. This is a major advantage over k-means, which assigns every point to some cluster. So in k-means, every point is assigned to a cluster, whereas in DBSCAN, anything. So you can have outliers, noise. Noise points often correspond to outliers or sparse regions in the data, regions that are not so densely packed together. So you have strength of DBSCAN over K means number one, talking about number of clusters, right? DBSCAN automatically determined from data. For K means it must be specified beforehand. In fact, the best way to know is using the elbow method or the silhouette score. For cluster shape, DBSCAN can detect arbitrarily shaped clusters, but K means assumes spherical clusters all the time, like the examples we did previously. Noise handling, DBSCAN identifies noise points explicitly, while K means has no noise detection. All points are clustered. Initialization, DBSCAN is not sensitive to initial parameters, while K-means is sensitive to initial centroid placement. Density variation, DBSCAN can struggle if clusters have very different densities. K-means has poor handling of clusters with varying sizes and densities. Computational complexity, typically it's big O n log n with indexing structures for DBSCAN. For K-means it is O or n by K by iterations, and it is generally faster. So now let's use DBSCAN on iris dataset. Of course, that's like the most common dataset we've been using since we started machine learning, talking about supervised and now unsupervised. So the iris dataset contains 150 samples of iris flowers with four features: sepal length, sepal width, length, petal width, and of course, don't forget we have three species of versicolor, setosa, and virginica. So for visualization, we use the first two features, sepal length and sepal width, for easier visualization. Let me get the line numbers in place for easier referencing for the code. Step-by-step implementation and parameter selection. Now look at this. Important. So of course, you need to do NumPy, Matplotlib, all that. We've been doing this a lot. So sklearn.cluster, we need DBSCAN in this case. We do preprocessing with standard scalar. Then sklearn neighbors, we need nearest neighbors. Now, nearest neighbors, we're bringing nearest neighbor because we want to compare DBSCAN with nearest neighbor at some point. And then we are using classification reports and adjusted rand score for evaluation. Then since you're using the iris dataset, so you have iris dataset, load iris, then you have x iris.data, and you have this dot two. So here, because you're focusing on sepal length and sepal width alone, and the petal length and width are not, we're not bothered about those. Then we have y underscore true. You have iris.target, so you have true labels for reference only. Now because talking about unlabeled data, so this target thing is just for label for reference only, not like it's necessary, like that. So you have to standardize features important. This is important for distance metrics. So use the scalar, and so the X scaled now is scalar.fit transform of the iris data you have selected. You transform into a normally distributed variables. So you have parameter of minimum point. So minimum samples minus, and then common heuristics. You have two times dimensions. That's four. So since you are using two dimensions now, sepal length and sepal width, so the minimum point should be like two times two. That's four. So in that case, we can then create k distance plot to choose epsilon. So you have neighbors, nearest neighbors, n neighbors equals minimum points. Neighbors fit, you have neighbors.fit x scaled. Distances indices, neighbors underscore fit dot k neighbors x scaled. K distances, you have np dot sort distances, like that. So here you can easily get the right value of epsilon that is required. So then you have a figure here which shows you points sorted by distance on the whatever nearest neighbor based on the minimum points now. Then you have y label minimum point nearest neighbor distance, coming from the minimum point to the title. You have k distance, you have to select the value of epsilon. That's what that is doing. So from the plot, select epsilon near the elbow point. Now, depending on what we have, I may have to come and change this later. Depending on what this plot gives us, anyone near the elbow point is what we can choose. Then you can then run DBSCAN for this. So DBSCAN is DBSCAN. That's the model we are really using. So epsilon is epsilon, minimum samples is minimum points. Clusters is DBSCAN. So this is where we fit the model. DBSCAN.fit predict X scaled, the scaled model that is not normally distributed. The number of clusters excluding noise. So you have n clusters is length, set clusters minus one. If minus one in clusters, else zero. So n noise is least clusters, count minus one. So here we are sorting noise out of real clusters now. Then you print estimated number of clusters, that's n clusters. Estimated number of noise point, that's n noise. Then you are visualizing clustering results now. Plot figure 8 by 5, unique label, set clusters, colors, you have all this now. You have unique labels like that. So for label, you have color in zip, unique labels, colors. If label is equal to minus one, so that's black color for noise. So anywhere that is noise goes with black color, and you have column 0001 like that. Then you have class member mask. By the way, I think, yeah, okay, this is a for statement. So you have class member mask, cluster is equal to if cluster is equal to label, we're asking that question. Then you have XY is X scaled class member mask that we have here. Then you plot the scatter plot XY, all this. the noise, edge color, and all that. So the plot title, DBSCAN clustering on iris datasets, blah blah blah. So you can run this now. You can already be sure that it's not it's going to be a bit tedious compared to okay, I mean we've got our result now. So first of all, you have the K distance graphs to select uh the epsilon, right? So when you talk about the elbow, right, that point where so the elbow seems to be somewhere around here, maybe it's about 0.4 to 0.6, like that. So estimated number of clusters that we have got from this, I think, yeah, based on what we have now. The estimated number of clusters is 3, estimated number of noise points is 35, like that. So, so this is point sorted by distance to fourth nearest neighbor, like this. Then fourth nearest neighbor distance. So if you look at the elbow, that looks like something around here. But of course, what we have determined the number of clusters and estimated number of noise points. So since we are taking 3 points, so that'll be 0, 1, 2, and noise will just be black, right? So cluster 0, you have all these red ones. Cluster 1, you have the yellow ones. Cluster 2, you have green ones, which are few, and you have all the noise since they're not so close by all the other clusters. So in that case, you have sepal width standardized here, sepal length standardized on this other play, the x-axis like this. So we have that clustering done that way. So interpretation of the result, the algorithm discovered clusters based on density. Number of clusters may differ from true species count. Some points are labeled as noise, that is, those ones black, indicating outliers of points in sparse areas. Clusters can have irregular shapes. The flexibility makes DBSCAN suited for data where clusters aren't spherical or equally sized. So in K nearest neighbors, we assume spherical clusters, assuming that all of them are together, and noise is not distinguished. So so if you want to compare to k-means on the same data, we've done this before, you go through the same process. I mean, line 1 to 5, they are just to prevent an error message coming. But the real thing now, you have k-means. So k-means, you train the data on k-means again, on a scaled uh, k-means. And then we run this now, right? And we have this. So you see, there's no distinguishing noise here. We just have 3 clusters all together. So in this case, k-means forms exactly 3 clusters, which are already predefined. As you can see here, we have set number of clusters to be 3 here, predefined, right? Then clusters are convex and spherical around centroids. So if you get the centroid somewhere in the center, you can see that no noise is detected. All points belong to a cluster. So all the noise are matched together in clusters. So it performs well when clusters are spherical and well separated, but poorly when clusters are irregular or noisy. So this particular data, from to me, I think it's really noisy. So the best data you could have used is that of the first video I made on K-means, we had uh some synthesized data, and they look really compact together, spherical and together in clusters like that. It performs well when clusters are spherical and well separated, but poorly when clusters are irregular or noisy, which I feel this one is. At least this one is noisier than the synthesized data. Of course, that's also not real because it's made up. So summary and recommendations. So you need to understand your data, right? So know the dimensionality and distribution of your data set. Then choose minimum points. Use heuristics minimum points like 2 times number of features. So if you're using 2 features, so your minimum point should be double of your minimum number of features. Then you can generate k distance plots. So plot sorted distances to minimum points nearest neighbors to find epsilon. Then select epsilon, pick epsilon value at the elbow of the k distance graph. Then run DBSCAN, execute clustering with chosen EPS and minimum points. Then you're going to analyze the outputs, examine number of clusters, noise points, and cluster shapes. Compared to k-means, evaluate if DBSCAN better captures data structure and noise, right? So if you're interested in isolating noise, DBSCAN is the go-to place for you. So DBSCAN is a powerful clustering method when the number of clusters is unknown. Clusters have arbitrary shape and density. Data contains noise or outlier. So if you know the number of clusters, you may want to go for k-means. But if you don't know the number of clusters, you can use DBSCAN. So for the iris data set, DBSCAN effectively reveals density-based clusters and noise points that k-means cannot detect. Proper parameter, I guess I want to bring this down. Yeah, I think this works better. Yeah, this way. All right. So for every data set, DBSCAN effectively reveals density-based clusters and noise point that K-means cannot detect. So proper parameter tuning, like using K-distance plots, is essential for success. And with this, again, we come to the end of this video on density-based spatial clustering of applications with noise, DBSCAN, density-based spatial clustering of applications with noise, DBSCAN. So the beauty of this is that you can easily detect noise or outliers in your data if that's of really of significant importance to you, if it is significant to you, or if it is important to you. So we've come to the end of this. Let me know how helpful this video is for you. And of course, don't forget that you can easily download all my code sheets and data sets by following the description box. You find a link to my Google Drive where you can download everything and follow step by step so that as I do it, you do it. If you see a number, change it and see the effect it has on, run it and see the effect it has on what you're doing. So that way you can know what exactly each one is doing like that, right? So that's how that goes. If you have not subscribed already, you know you'll be missing a lot. So go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. And you want to go a step higher by becoming a member of my channel. There are 3 levels right now with different benefits. So check them out and see. Just click on join and you see the possibilities of how you can join. Be sure to like and share this video and other videos so that people who are interested, more people can have access to this great content I have going on here. Till I come your way again, keep doing data right. Bye.